Okay, this video is about the statistical tests for regression. You may have noticed that the last video didn't have any actual statistics in it. There was no hypothesis test or distributions to look at. We're going to fix that in this video. Our hypothesis test is going to determine whether or not a linear trend even exists. Before we can talk about the hypothesis test, we have to define our parameters. So let's take a quick tour of parameters and their estimates we've already seen. The Greek letter mu is the population mean, and it is generally estimated by the sample average, or x bar. The letter p is the population proportion, and it is estimated by the simple proportion p hat. The Greek letter sigma squared is the population variance, and it is estimated by the sample variance s squared. These are the parameters that we've already dealt with at various times during this semester. And now we're going to add a new parameter, the Greek letter beta 1, or the population slope coefficient. And this parameter is estimated by the slope coefficient of the best fit line. The hypothesis for regression is all about the slope coefficient. This will determine whether or not there actually is a relationship between x and y. We begin by assuming there is some straight line relationship between x and y, which depends on these parameters, beta 1 and beta 0. Beta 1 is the slope of the line, and beta 0 is its intercept. As usual, we begin with no knowledge of these parameters, so we collect data and try to estimate them. After collecting our data, we can calculate the best fit line as an estimate of this true but unknown line. And here's the crucial fact. If there really is no relationship between x and y, then the true slope coefficient would equal 0. A slope of 0 would mean that the y variable has no dependence on the x variable and hence no relationship. So in order to test for a relationship, we need to assume in the null hypothesis that there is no relationship, that the true slope is equal to 0. And if we reject the null hypothesis, then we can conclude that there is a statistically significant relationship between the variables. You may have been suspicious in the last video when I started talking about the residual sum of squares. Your alarm was right. There is an ANOVA table behind the hypothesis test, and the residual sum of squares is a part of it. So hopefully you were paying attention during the last video. Anyway, our regression ANOVA table has 3 rows: regression, error, and total. And the degrees of freedom are 1, n minus 2, and n minus 1, where n is the total number of data points. All the usual rules for the ANOVA tables are the same, and everything will flow towards the f value. That will determine whether or not we reject the null hypothesis. And even though the alternative hypothesis from the previous slide appears to be two-tailed, ANOVA critical values and p-values are always one-tailed, right-tailed, so we don't have to worry about that. The ANOVA sums of squares calculations are pretty straightforward. They rely on 3 things: the data points, the best fit line, and y bar. And the calculations have a nice visual quality too. I'm going to demonstrate with the data point 4,9 up here. The y value of any data point is simply called y in the calculations. We already have the best fit line drawn in our graph, but we also need a horizontal line at y bar, which is equal to 5. Now, if we move down from this point, and there is a point on the best fit line directly below our data point. The y value for this or any other point on the best fit line is called y hat. Move farther down, and there is also a point on the horizontal line. The y value of this point is called y bar. There are three distances that will be important for us. First, there is the distance between y hat and y bar. This is used in the regression sum of squares. Second, there is the distance between our data point y and y hat. Remember that I called this distance the residual in the last video, and this is used in the error sum of squares. And last, there is the distance from the data point y all the way down to y bar. This distance will be used in the total sum of squares. Since many numbers are used multiple times, I find it easiest to put all the calculations into one big table. We already have our data points on the left, and the next column that we're going to make is y hat. So we're going to find points on the best fit line directly above or below all of our data points. So for each data point, take the x value and plug it into the best fit line equation. You should get these values for y hat. Now let's also remember that y bar is equal to 5. Now we're going to start doing the sums of squares calculations. We'll begin with the regression sum of squares. The formula uses only y hat and y bar. First, we'll subtract y bar, or 5, from every y hat value to get these numbers. Next, we'll square them to get these values. And the sum of these squares is equal to 25.6. And that is our regression sum of squares. Next, we'll do the error sum of squares. The formula uses only y and y hat. First, we'll find y minus y hat for each point. These are the residuals. Next, we'll square them to get these values. And the sum of these squares is equal to 14.4, and that is our error sum of squares. So the error sum of squares is what I called the residual sum of squares in the last video. Some books call it the residual, others call it error. It's the same thing. Finally, we'll do the total sum of squares. The formula uses only y and y bar. First, we'll subtract y bar, or 5, from every y value to get these numbers. Next, we'll square them to get these numbers. And the sum of these squares is equal to 40, and that is our total sum of squares. And you can see that, as usual, the other sum of squares add up to the total sum of squares. Let's go to our regression ANOVA table, and we can plug in our sums of squares that we just finished calculating. And since our data has 5 total points, our degrees of freedom are 1, 3, and 4. We find the MS as usual by taking sums of squares, dividing by degrees of freedom. And finally, the F value is the MS for regression over the MS for error, and it's equal to 5.33. And this F value comes from a distribution with 1 degree of freedom numerator and 3 degrees of freedom denominator. If you look up the 5% critical value in the F table in your book, then you'll see that the critical value is 10.1. So our F value is not big enough to reject, and we would conclude at the 5% level that there is no relationship between our variables. And let me make one more side note about this example. An F value bigger than 5 is usually results in a rejection. The main reason why this example doesn't reject is that we have a very small sample size and therefore also very small degrees of freedom. There is also a t-test option to perform the hypothesis test. It doesn't do anything new, nor does it make the calculation any easier for us, but it does show us a different side of the hypothesis test that is interesting. Here is our original hypothesis, and now it actually does matter that this is a two-tailed hypothesis because we aren't using ANOVA anymore. And here is the T formula. It follows the basic structure of any T formula. It has an estimate subtracted by its mean, all divided by some square roots, which is a standard deviation. The formula is focused on B1, the slope of the best fit line. The mean of B1 is beta 1, and this big square root is its standard deviation. Although most books prefer to call it the standard error, it's the same thing. One thing that sticks out right away is that the standard error uses the MSE from the ANOVA table. So there's no way of doing the t-test without first doing the ANOVA table. Pointless, right? But let's continue on with the calculation anyway. In later classes, the t-test will be important. Let's plug in all the numbers. The slope of the best fit line is 1.6. The null hypothesis is that beta 1 is equal to 0. The MSE from the ANOVA table is 4.8. And the sample variance of x was 2.5. You can verify that from the last video. So we end up with a t-value of 2.3094 with 3 degrees of freedom. Why 3? Because whenever you plug in the MSE into a formula, you bring along its degrees of freedom. And the error row from the ANOVA table had 3 degrees of freedom. If you look up the t-distribution with 3 degrees of freedom, then you'll see that the two-tailed 5% critical values are plus and minus 3.182. Our t-value isn't big enough to reject, and the thinking behind this test is that B1, the slope of the best fit line, simply isn't big enough to be significant. Before we end this video, there are a couple of side points that need to be addressed. First, we're going to return to the coefficient of determination again. In the last video, I defined the coefficient of determination, or R squared, as the sample correlation squared. And that's still true, but it's also equal to the regression sum of squares over the total sum of squares. This is a trivial point in simple linear regression, but it's a really important point later on. And since the regression and error add up to the total, it can also be written like this. And the regression sum of squares represents the explainable variance, while the error represents the unexplainable variance. I'll explain more about that in class, but this language at ANOVA still applies and is commonly used in research papers. Our last side note is that there's a direct equivalence between the ANOVA F-test and the t-test that I showed you. Our F value of 5.33 is actually equal to the t-value squared. This is not a coincidence. An F distribution with 1 degree of freedom numerator is always equivalent to a t-distribution squared. So the N of the f-test and the t-test are actually just 2 different forms of the exact same thing. Even the critical value of the f-test is the square of the t-test critical value. They are completely equivalent in simple linear regression. And finally, here is the piece of sales data again from the last video. The complete data is shown over here on the left, and the best fit line is shown in the scatter plot. You should copy this data down since you'll need it to answer the 3 questions coming up. Good luck with that, and I'll see you in class.